if you take a look at this problem, it really doesn't require that much of an explanation. It said Newton had an incorrect theory of gases in which he assumed that all gas molecules repel each other in the walls of their container. Thus, the molecules of a gas are statistically or statically and uniformly distributed, trying to get as far away from apart as possible from one another and the vessel walls. This repulsion gives rise to pressure. Explain why Charles' law argues for the kinetic molecular theory and against Newton's model. Well, obviously, Newton's model attempts to explain pressure, but what it doesn't explain is any effect that temperature has, and that's what Charles' law is based on. So Charles' law, you guys know that Charles' law is when we have temperature increase, what happens to the pressure, what happens to a constant pressure is like what we're looking for the effects of what happens to volume. Now, Boyle's law is the only one that's inversely proportional. So Charles' law, the volume goes up when temperature goes up. So if you increase the gas inside a balloon, the balloon's volume will also increase to keep a constant tension on the outside of the balloon. Now, that's not a perfect example, but it's one that works pretty well for us. So we would expect, if you would have a temperature gauge inside a piston, then you would have the piston increasing in volume as under constant pressure if you increase the temperature's gas inside the piston. So that would be another good example of Charles' law, where volume changes dependent on the absolute temperature change. So my answer to this then would be that Newton's law, Newton's theory, does not handle temperature at all. Does not. So under Newton's theory, gases wouldn't change. So this says under Newton's theory does not describe, that's what this says here, I know that's awful, does not describe temperature change within the theory itself. So that would be a major failing from Newton's theory. So the kinetic molecular theory says that with the increase of the absolute temperature of a gas, you have an increase over an average increase in the speed of the molecules that are moving. So the kinetic molecular theory actually makes a prediction as to what's going to happen to the gas molecules when you increase the temperature. Newton's theory does not. Okay, so let's move on from that because that's really the difference between the two, or a major difference between the two. So let's take a look at 76. So it says, place the following gases in order of increasing average speed at 300 Kelvin. Okay, so this is increasing average speed. So the first thing we need to do is we need to go through each one of these and take a look. I have 12. All I'm going to do is find the molar mass of each one of these. So all I'm doing is taking one carbon, because there's only one carbon in CO, adding it to one oxygen, which is 16, so 12 plus 16 is 28, and that's grams per mole. Okay, so that's the number we're going to focus on. SF6 would be 32.1 plus, and then 19 times 6. I should actually know 19 times 6. We've seen this a ton of times so far. It's 114. So we're going to add 114 to 132 to get 146.1. Okay, let's keep going. H2S, that's 2 for hydrogen and 32.1 for sulfur, so that's going to be 34.1 for H2S. For Cl2, I get 35.5 for each chlorine, so 71 is what I get for that. And then finally, HBr would be 1 plus 79.9, which I'm going to round up to 80. So that's going to be an 81. So all I have to do now to put them in order increasing average molecular speed would be to start with the highest, which would be SF6, and then larger in speed than SF6 would then be HBr. Larger in speed than HBr would be Cl2. Larger in speed than Cl2 would be H2S. And then finally, the last one is that. Excellent. So then it says calculate and compare the RMS speed U for CO and Cl2 at 300 Kelvin. So this is going to take a little bit of, I told you that we weren't going to do a calculation like this. You won't see a calculation like this on the test. I just thought maybe it was worthwhile having you look at one because we have to do a little bit different thing here with the R value. So let's take a quick look at 76B. So the first thing we're going to do is we're going to find the RMS speed for CO. And that's going to look like this. We're going to use this equation where we have 3RT, and all of that's going to be divided over the molar mass. So here's what it looks like when I pull the whole thing out. That's going to be equal to, now I got 3 times. Now, here's the deal. The problem is that I'm going to be using the R value is going to be the 8.314, but it's not going to be, this is going to be the change up. It's not going to be kilopascals. Another way that kilopascals can be written is by using force units. And force units, and you wouldn't know this, of course, unless someone explained it to you, is going to be meters squared divided by seconds squared, and then that's, hang on a second here. Good, okay. Meters squared, seconds squared. And then notice that we have kilograms here, and that's going to be a problem later on. We're going to have to change something for this, and then we're going to multiply by, oh, and that's, of course, divided by mole. Yeah, let's just keep going here. Times 300 Kelvin, like that, because it gives us 300 Kelvin. All of this is going to be divided by, now notice I have the kilograms, and here's what I was talking about. The M here is for molar mass, and molar mass is in grams per mole. Okay, now here's what I need to do. If I want to change this to kilograms per mole, which we can, kilograms per mole means I would be multiplying whatever the grams are times 1,000, and that would give me kilograms. So instead of CO up here, up there, oops, that's the wrong one, that's HF. CO is 28 grams per mole. If I change that, I can do 28,000 kilograms per mole. I did that the wrong way. Decimal point goes in the opposite direction. Sorry about that. It's been a while since I've done one of these. So 0.28 would be, I swear, I'm losing my mind, 0.028 kilograms per mole, like that. Okay, so now I put all of this together, and this is going to be to the 1/2, which means square root. So I multiply all of this out, take the square root of that, and what I end up with then is going to be 5.17 times 10 to the second, which means 517, and that's going to be meters squared per second squared. It would be, except we're taking the square root of all of those. So that'll be just meters per second. I do the same thing. Sorry, that was brutal. I know that was, I know that took forever. So let's go through the next one just a little bit quicker. And we'll find U for Cl2, and that's going to be the same thing, 3RT over molar mass equals, and then the 3 stays the same, the 8.314 stays the same, the 300 stays the same, like this. The only thing that changes really is going to be the 80 71 grams per mole. Now, the 71 grams per mole means that I need to change that to 0.071, and that's kilograms per mole, like that. Okay, remember we're changing this to so we can cancel the kilograms on top of the kilograms on the bottom, and all of this is going to be to the 1/2, which means that I end up with 325, and this is also going to be meters per second. Notice that the lighter molecule is in fact a lot faster than the other one. All right, that's it for 10B problems.